Hello. The lecture of the today is maximum power and superposition theorem. These are other two network theorems before we start op-amp lectures in the next class. Today we'll see into one port network, and if we put a load resistance across that one port network, we'll look into the answer of what load will draw maximum power from that one port network. So let's start with the revision of the one port network. So this linear network with two open terminals, this is the representation of one port network, and let's say we have a load RL connected to that one port network. Our interest with the maximum power theorem is finding RL that gives maximum power across this terminal and calculating that maximum power. Okay, so since this is one port problem and we already have been through the lecture on source transformation, we can utilize Thevenin or Norton equivalent circuit to solve this kind of circuits. So let's transfer this into Thevenin equivalent, which will be this is VTH Thevenin equivalent, it's RTH, and we have our load RL. And let's say the current flowing across this circuit is IL. Okay, in that case, using the voltage divider rule, we don't need to use voltage divider, we can just do voltage divider resistance because these two are in series to find the current, right? So we can IL, so we can calculate IL is VTH divided by RTH plus RL, and the power that is absorbed by RL can be written as IL squared times RL, right? Because power is I squared R, and since our I is this term here, equation 1, so we can substitute that here, then power will be VTH squared times RL divided by RTH plus RL squared, right? Let's say this is equation 2, and we know that for any equation to give us the maximum or minimum value, the first derivative should be equal to 0. So for maximum power, we'll have to do dPL divided by dRL is equals to 0. So if we take the derivative of equation 2, we'll get RTH plus RL squared minus 2 VTH squared times RTH plus RL times RL divided by RTH plus RL to the power 4, right? And we can simplify it. R0 is equals to VTH squared times RTH plus RL minus 2 VTH squared times RL, because we can take this RTH plus RL common factor and cancel out. That will leave us to the power 3 in the denominator. So for this equation to be 0, right, we can see that this part need to be 0, and that means we can cancel out VTH square, take this out from the equation. That will give us 0 is equals to RTH plus RL minus 2RL, or basically that implies RTH is equals to RL, and that is our maximum power theorem. So for the one port network to carry maximum power, the load resistance should be equal to the Thevenin resistance. That is the maximum power. So let me write this, highlight this. Maximum power transfer theorem, and this is what we're going to look into the lecture today. And since we know that RTH is equals to RL, we can substitute this value into the power equation here in the equation second. That will give us VTH squared times RTH divided by RTH plus RTH squared. So then the power, so the maximum power now, maximum power will be PL max is equals to VTH squared times RTH divided by RTH plus RTH square, basically replacing RL by RTH here and here. And if we simplify that, that will give us VTH squared divided by 4RTH. So if you have a one port network and the load connected is RL, then the maximum power that can be absorbed by that load is VTH squared by 4RTH. Okay, now this information should be enough to solve one example problem. Let's see the example problem. Okay, here is the circuit. And this is all linear. Here is the resistance. For now, let's consider is variable resistance because that is something we need to find to get the maximum power. The current here is 30I delta. This resistor is 40 kilo ohms. This one is 10 kilo ohms. This one is 50 kilo ohms. This is 5 kilo ohms. The current here is, the resistance here is 20 kilo ohm, and this current source is dependent on the current across here, which is I delta. This is the 2 kilo ohm, and we have a voltage source of 40 volts. So this is the circuit given, and we are to find the value of R naught and the maximum power. So find the value of R naught required per maximum power transfer. That is the question A, and question B is find the maximum power. So this should be pretty straightforward because we have already dealt with this kind of circuits, and we know how to make the Thevenin equivalent resistance by finding the Thevenin equivalent voltage and resistance. So once we find that, the only thing we need to do is put these values into this formula and get the PL max, and R naught is basically RTH. So let's do that. Now we know that alternate method, and for the alternate method for the calculation of RTH, we need to either determine the open source voltage or the short circuit voltage, right? So if you remember, RTH is equals to VOC divided by ISC, right? So, and VOC is equals to VTH, right? And then if we have to determine the Thevenin equivalent, we just need VTH and RTH. So what we can do is we can find RTH from alternate method, and if we can find either ISC or VTH, then we can determine VTH, right? So in this case, let's try to find the short circuit current of this one port network. Okay, so what we're going to do is we're going to short circuit the one port terminal and look into the problem and try to find the ISC. Okay, if we short circuit here, so let's say I'm going to redraw this, but let's say if I'm going to short circuit this part, you'll notice that the current can bypass this 40 ohm resistor, and this 40 ohm resistor will be obsolete. Okay, let me draw the circuit with short circuit. Let's do this. Find ISC of one port. Okay, that is our first step, and then in the second step we'll find the RTH, and then we can, using those two equations, we can find VTH. Redraw the circuit. But then this time you only have you don't have this 40 ohm resistor, because once you short circuit, that is not useful at all. So plus minus, this was 40 volts. We had another resistor here. This was 2 kilo ohms. This was 20 kilo ohms, and the current source 30 I delta was dependent on the current I delta here, and we had another resistor of 50 kilo ohm here, 5 kilo ohm here, and 10 kilo ohm here, and then the 140 ohm we had here, that is no more here because of the short circuit. And let's say the short circuit current is ISC. So we can solve this problem using loop current method. You see, if let's say if I have current I1 flowing here, current I2 flowing in this loop, then in this loop we'll have the current ISC, right, because this is the short circuit, and in this loop we have current 30 I delta. Okay, and then we don't need to determine the voltage across this location, so we can skip this part because we'll have three equations and three unknowns, I1, I2, and ISC, and basically I delta is I1 minus I2, so we don't need the fourth one either. So we'll apply KVL to solve this problem. Okay, let's start with KVL around loop 1. Okay, KVL around mesh 1. Okay, and for the outer loop we can just randomly assign the directions to the directions of the current, right? So these are the outer ones. We can assign the direction of current like that. And KVL around mesh 1 will give us, let's start from here, that will be minus 40 volt, right, plus we have 2000 ohms times I1, that is the current there. Then we have 20,000 ohms times the current I1 is following down and up is 2 is up, so you have I1 minus I2 is equals to 0 because that closes the loop. So let's say this was our equation first. Okay, then we can write KVL around mesh 2. Okay, and then if we start from here, you have 20,000, that is I2 minus I1, and then you have 5,000, this one, which is only I2, and then you have this 50,000, which is I2 minus ISC, right, plus 50,000 I2 minus ISC is equals to 0. That is your equation second. And now we write the KVL around this ISC loop, mesh 3, KVL around mesh 3. So we can write KVL around mesh 3 is 50,000 ISC minus I2 plus 10,000 ISC minus 30 I delta, because that is the current coming from here. That will give us 0, right? So we can write that as 50,000 ISC minus I2 plus 10,000, that was the resistance in the upper loop, and ISC minus 30 I delta is equals to equation 3. So we have I1, I2, ISC, those are three unknowns, And I delta is easy because I delta is basically looking into this loop. I delta is I1 minus I2, so I delta is equals to I1 minus I2. If you substitute this in here, so if you substitute this value in here, you'll have three equations, three unknowns, and you can solve for the currents. You don't have to find all those three currents, you just need ISC. Okay, and I'll just write the answer here. So if you solve this, you will get ISC as 14 milliampere. Okay, wherein solve those three equations. Once we have the short circuit current, now we can use the alternate method to find the Thevenin equivalent or R equivalent. So let's use the alternate method to find R equivalent, or which is equals to R Thevenin or R Norton, right? And then the first step here was to zero the independent sources. So for voltage source we short circuit the voltage source, and for current source we open circuit the current source, right? So in this case, now we have the original problem here. So in this case, what we are going to do is, now we don't need to take this into consideration because our idea is to find this R equivalent. So we're looking from this side, and this is our on port from here towards this side, right? And since we need to find RTS, we need this. And since we are trying to zero the source for this 40 volt, we zero it by short circuiting. And once you short circuit, I will redraw the rest of this figure below with 225, 50, and this part and 40. Okay, so let me redraw the circuit again. Okay, so this was our input, and across this one we had the current controlled current source 30 I delta, right? And this one was 10 kilo ohms, this one was 40 kilo ohms, and this one was 50 kilo ohms, this one was 20 kilo ohms. This current was I delta, this was 2 kilo ohms, this was 5 kilo ohms, right? So basically same figure without R naught and without the voltage source. And now since we are zeroing, we short circuit this voltage source, right? And the second step of the alternate method to find RTH was supplying a source, either current source or voltage source, and finding the other one. So here we can apply a voltage source with V test, and if you remember, a good number to have a test voltage source is 1 volt, right? And then if that case, let's say this will be your I test, right, the current flowing. So once we know I test, your RTH is basically V test divided by I test. So we're going to do that here. So now look into this circuit, we can say that node voltage would be a good method, because then we have this many common node here, right? Everything from here to here, that will have zero voltage. So let's take this as V reference is equals to 0, right? And then we can apply the node voltage method here. So for node voltage method, we need to assign current directions, right? Let's assign these directions randomly, and then since already down, so I'll just write plus minus, again plus minus, plus minus. Let's assign this direction, plus minus, and I test, we're applying this side. So if V test is 1 and this is 0, so you can agree that at this point you will have 1 volt, right? And this point also 1 volt, right? No, sorry, this point we have 0 volt. Sorry, this is the reference. And then the only unknown nodes are this and this. So let's call Vx and Vy for these two and apply KCL at these two x and y node to see if we can get the values of the voltages and then use that to get I test. Okay, so let's first apply KCL at node x. Okay, so looking into this figure, KCL at node x, so 0 minus Vx, right? 0 minus Vx divided by 2000, right? That is the current entering and leaving are these two, right? Is equals to Vx minus 0 divided by 20,000, right? Vx minus 0 20,000 plus Vx minus Vy, this difference, divided by 5,000. Okay, so we have one equation, right? And let's write KCL at node y. Then looking into node y, okay, this is y, so current entering is Vx minus Vy by 5, one current leaving is Vy minus 0 divided by 50, other one is Vy minus 1 divided by 10, the other one is going this direction, which is 30 I delta, right? So we just try that. Vx minus Vy divided by 5,000 is equals to Vy divided by 50,000 plus Vy minus 1 divided by 10,000 plus 30 I delta. And we know this I delta comes from this part of the circuit, right? So this is here, so that is basically Vx minus 0 divided by 20,000. So if we replace that, then we have two equations and two unknowns, right? Let's say this is second equation and there are two equations, two unknowns, but this is known because you can replace that with I delta is basically Vx divided by 20,000. So if you replace that, you have Vx and Vy, and you can easily solve this. I'll leave up to you to go ahead and get the values of Vx and Vy. So the next step, solving for Vx and Vy, you'll get some values here, and our task here to find the I test, right, which can be found if we apply KCL at this node. So KCL at, I will say, node A. Okay, if we apply KCL at node A, you have current entering, which is 1, is this one is entering, I test is entering, you have 30 I delta that is also entering, and the only current that is leaving is this one, 1 minus 0 divided by 40, right? So we'll go ahead and write that here. KCL at node A. KCL at node A. So if we do that, we can write that as I test, that is entering, plus 30 I delta, which is 30 Vx divided by 20,000, right? Plus Vy minus 1 divided by 10,000 is equals to 1 divided by 40,000. Okay, and then we already have Vx and Vy from earlier step, and that should be pretty straightforward. And if you solve this, you should get a value of 50 microampere. So basically 50 times 10 to the power minus 6 ampere. Okay, so now we can easily determine R equivalent is equals to R Thevenin is equals to V test divided by I test, and our V test was 1 volt divided by 50 microampere. That will give us 20 kilo ohm resistor. Okay, now we have everything to construct the Thevenin equivalent. So let's first construct the Thevenin equivalent. Okay, so this is the Thevenin resistance. We just calculated 20 kilo ohm, right? And the source voltage here VTH should be equals to ISC, short circuit, times RTH, right? That is, the short circuit voltage we calculated was 14 milliampere times 20 kilo ohm is equals to 280 volts. That should be the voltage we get here. And finally, if we had R naught here, so for maximum power, we know that for maximum power, we know that R naught should equals to RTH. That will be 20 kilo ohm, right? And then the second question was finding the maximum power, right? So PL max would be VTH square divided by 4 RTH, and that would be 280 times 280 divided by 4 times 20 times 1000 ohm, right? So that will give you 0.99 watt, 0.98 watt. So that is our final answer. Okay, so that is one of the topic of the day today, maximum power. We have one more theorem we need to look before we move to op-amp lecture for the next week. That is the superposition theorem. It's not very often used in direct current analysis with only the resistor element, but once you move to AC circuit, sometimes superposition is the only method that is viable, and this is really commonly used technique. So we'll have a look into this network theorem, which is called a superposition theorem. So what it says is, given a linear network, any circuit voltage or current may be calculated as the algebraic sum of the individual voltages or currents caused by its independent source. Acting alone. So if you have more than one current or voltage source, and if we trying to find the effect of that only one voltage or current source at a time, then it says that the total effect produced will be the sum of those two effects. Okay, so let's directly jump into an example and see if we understand that from there. So the question asked is, use superposition to find the voltage V. Okay, and our circuit looks like this. You have a current source with 4 ampere, okay, and then you have a voltage source that is 110 voltage. You have a resistance here, you have another resistance here, another resistance here. This one is 10 ohm, this is 12 ohm, I guess. This is 2 ohm, this is 5 ohm. Okay, so now by this point we know that whenever we deactivate current source we open circuit, and whenever we deactivate a voltage source we short circuit it. So let's do that. We activate one source at a time. So we start with activating the voltage source first. Let's activate 110 volt source. Okay, that means we have to deactivate this 4 ampere source, and that means open circuiting that's 4 ampere, right? Because open circuits the current source are open circuited. That will give us our new circuit is this 12 ohms, 2 ohms, 10 ohms, and then you have your voltage source 110 volts. Okay, this is 5 ohm. Now if we make an equivalent circuit, we can calculate voltage using voltage divider rule. What I'm saying here is let's say we have this 110 voltage source, and if I had this 5 ohm here, and rest of everything combined is just one resistor, then we can find the voltage across here, and now call this as B dash. Then we can calculate that voltage V dash using the voltage divider rule. So for that we need to first calculate this equivalent resistance. So that is the equivalent resistance between these three resistance. So you can say that in this circuit 2 and 12 are series, and the sum of these two are in parallel with 10. So if we were to find one equivalent for these two, which is this, will be this 2 and 12, which are in series, 2 plus 12, right? And then those two are then in parallel with this 10 ohm resistor, right? That will give us the equivalent resistance 5.833 ohm for this resistance. And then now if we use the voltage divider rule, we can calculate V dash as the source voltage, which is 110, times this resistance divided by the equivalent resistance, which is basically the series combination of these two, and that will give you 59.23 volt. Okay, so now we saw the voltage that is generated using that voltage source only. Now let's see what is the effect of the current source, 4 ampere current source. Okay, so if we are going to activate the current source only and deactivate the voltage source, you might already know that we'll be going to short circuit that voltage source, right? So the voltage source here, there was a voltage source there, right? In our initial circuit diagram, we're going to short circuit that. And so now we are left with this diagram, and our voltage direction, that is from the beginning. The one thing to consider is that you have to have the same sign for voltage. Once you assign for the first problem, always do that from the same perspective so that you can just add those up. Okay, 5 ohm. So we can simplify this circuit as having, if we combine these two as parallel combination of circuits, they will have these two as series, and then this is left here, and we can use the current divider rule to find the current across here. And then the voltage will be and the voltage drop will be the voltage drop across these two, combination of these two, because it will be the same as long as it's in parallel, right? So what I'm saying here is you can convert this circuit into 4 ampere 12 ohm resistor, right? And you can just have these two resistors. 2 is here, and this is the parallel combination of 5 and 10. So 5 and 10, they are parallel, which gives you 3.33 ohms. okay, but then we still, as I mentioned earlier, we need to keep the sign same. So this side is positive, that means this side will be negative, right? Positive and negative, and that will be our V drop, right? V double dash. But looking into the current direction, we can say that the 4 ampere current is coming this way and is going to flow this way and this way, right? So the voltage technically will be negative. That means the voltage will, high voltage will be this side, the other low will be other side. So that is why we need to include the sign here, and we can use this as minus the current source, which is 4, and sorry, not 4, because we are going to divide that current, my bad. Let's first let's first calculate the current in this circuit, okay? So we need to calculate, let's say the current here is Ix, okay, and current on this side is Iy. So we need to find Ix to find the voltage drop there, and Ix can be used determined using the current divider rule, right? Ix is basically, if you have circuit like this and if it goes along this circuit and this circuit, you can write it as the current source 4 times 1 by, because these two are in series, right? And then the current divides between this and this, right? So 1 by 2 plus 3.33, which is 5.33, that divided by 1 by 12 plus 1 by 5.33, that will give you 2.769 ampere. Now we know the current, we can just calculate the voltage difference across this part is from this part to this part is current times the resistance, which is 3.33, right? And but that will be negative because of the sign. So V double double is equals to minus Ix times the R equivalent between those two, which was 3.33. So that is minus 2.769 times 3.33, which will give me minus 9.231 voltage. So the voltage across the 10 ohm resistor can be, now we can utilize superposition theorem. So this is the time to apply superposition theorem. So what that says is the voltage across this 10 ohm resistor will then be equals to V dash plus V dash, the sum of individual sources. So that one was 59.231 and this one was 9.231, and this is negative because the current is opposite direction of the assumed voltage, okay, in the first case. So that will give us 50 volt. So yeah, that was the topic for today. Next class we'll be looking into operational amplifiers. Thank you.